Hi everyone, so today we're going to be looking at uniform electric fields and how charged particles behave in those uniform electric fields. But before I start, I wanted to just simply go through how to investigate Coulomb's law. So we know that Coulomb's law states that the force is directly proportional to the product of the charges and inversely proportional to the square of the separation between them. So if I wanted to investigate his law and prove this relationship, I will need to be able to get two charged objects for charge Q and Q, capital Q and lowercase q. I will need to be able to measure the force and the distance between them as well. So I should devise a way of measuring this force and this distance between two charged objects. So in this case, we could simply use metal spheres. So two small metal spheres is enough. Obviously, we need to charge them somehow. And the way to do that is to just simply touch them momentarily to a positive electrode from a supply. So that will give them a positive charge. However, obviously metals are conductors. They allow electricity to flow through them. So they allow electric charges to flow through them. And in our case, we don't want the charge to flow through to the ground and be earthed. We want them to maintain their charge. So the only way of doing that is by connecting them to something insulating, so like a piece of wood, for example, or a plastic stick or something. So you could get the two spheres, you touch them to an electrode, positive or negative electrode. Let's say we touch them to the positive electrode using and connected them to, before we touch them there, we connected them to a plastic or wooden stick each. Now, I definitely know that positively charged spheres will repel each other, so they will go in opposite direction. I should be able to measure the force acting on one of them at least in order to be able to calculate and the distance between them in order to be able to figure out the relationship between them. In this case, I can use a balance, so I can place this on a balance. You will need to tear it, so meaning take it to zero as soon as you place it on there, because obviously the sphere itself will have mass and the stick or rod, plastic rod, will have mass when you place it. So you have to tear it first. And once you do that and you place this sphere close enough, you will get a reading on the scale because they repel. So let's call this sphere 1 and sphere 2. So sphere 1 will repel sphere 2, and then sphere 2 will press into the scale since it's pushing away. And you will get a reading. The reading will be a mass reading. And we know that weight is equal to mass times gravitational field strength. So weight is a force, again, as a reminder. So what we have is we can use the mass that we get times 9.81 to be able to calculate the force. Now, to get a distance, you can place a ruler fixed on a clamp stand, or have it an approximation with the eye. You will need to definitely mark in the centers of the spheres so that you can get the distance from the centers, if we are assuming that they're point charges, so all the charge is concentrated at the center, and that's how I can record force against R. So obviously you can change this distance by decreasing it or increasing it, whichever way you want to go, and then collect multiple values for force and separation. Now, to get the relationship, you just simply need to draw a graph of F against 1 over R squared. You should get a straight line going through the origin with the gradient being equal to, since this is y, is equal to mx plus c. what you will have is your y, 1 over r squared is your x, so your gradient will give you 1 over 4 pi epsilon naught, which is a constant times the charge of one of the spheres times the charge of the other sphere. And there is no y-intercept, so that shows that it has to go through the origin. So that's one example of one way of investigating it. I just thought I'll mention it before I proceed into uniform electric fields. So there will be a few things that we'll be looking at. It's a bit of a mathematical topic, and it's also a bit of a synoptic topic. So things that you have seen in projectile motion in terms of, well, it's not even projectile motion mostly, so also SUVATs. So things that you've seen in SUVATs we might come across. Things that we've seen in chapter 21, so capacitors will come up in this topic as well. And yeah, it's a very, very, very synoptic topic, so you should be able to pull in and use any information that you learn throughout the course to apply it. So to start with, we're going to be looking at a uniform electric field. So basically proving this equation, you need to be able to derive it too. We will look at the capacitance in terms of area, cross-sectional area and distance, and we're also going to introduce the term permittivity. So we will come across these equations, and we will analyze motion of charged particles in uniform electric field. So this is where we will see SUVATs, and we'll bring a bit of reminder back from SUVATs. So we have already seen in the first lesson that the electric field between two parallel plates is uniform. That means that the value of electric field strength is the same everywhere between the plates. Also, I've spoken about how we have the positive terminal, let's say in this case of the battery, connected to one of the plates, which gives it an overall positive charge. And we also have the negative terminal of the battery connected to the other plate, which gives it an overall negative charge. Now the charges are equal and opposite, so that means the field is uniform as well. And also we have air between the plates. In the previous chapter, we saw that a capacitor is usually made up of two plates separated by an insulator. So metallic plates separated by an insulator, usually a dielectric material. Dielectric materials usually have molecules that have a positive and negative side, and they just tend to align themselves with the field when you apply an electric field across the plates. So what we're seeing here is a simple form of a capacitor, basically, with air between the two plates. So you can see how now electric field combines a lot with capacitors topic, because between the plates of capacitors we have an electric field. And we, even though we have already defined the electric field strength to be equal to the force per unit positive charge experiencing the force in that field, we need to come up with a new expression that we can use values that we can measure easily from a circuit. So in this example, we know that the potential difference can be measured easily because we can place a voltmeter parallel to them, and the distance of between the plates can also be measured easily, depending how far away they are. So if they're quite far away from each other in terms of meters, then you can use centimeters, you can use a meter ruler or a 30 centimeter ruler. But if the distance is too small, you will either have to use ruler for large distances, micrometers, or vernier caliber for short, very small distances in millimeters, or a little bit less than that. So this is just simply how to take quick measurements. Now, why are we interested in expressing in a different way? Because, well, we can measure these values. And the way to begin with, if I want to measure the electric field strength using a potential difference in the distance, I need to come up with an expression that involves this one. So we already know that in chapter 9, and if you want to go back and recap chapter 9, lesson 1, we introduced the potential difference and what it means and how is it defined. This is one of the most common equations that people forget, or they forget what potential difference is in general. Well, potential difference is the energy transferred per unit charge. Simply, the energy given to each unit charge, or the energy given by each unit charge, actually. The EMF is the energy given to each unit charge. Potential difference is the energy given by each unit charge to a component. We also know that work done can be rewritten as force times distance. I know we usually write it as a S for displacement, but in this case I will leave it as D to specify that it's not displacement, it's actually distance. And yeah, that's just about what we need to come up with an expression that relates the electric field strength to potential difference and to the charge. So before I continue, let me rewrite this equation as well. So I have equation 1, have equation 2, and equation 3 can be rewritten as F is equal to E times Q. So this is the force, this is electric field strength, and this is the charge of, if I placed, for example, a positive test charge here, this is the charge that will experience that uniform electric field strength. So the electric field strength will be the same no matter wherever you place that test charge. So I will start by rearranging this equation. So that's work done is equal to potential difference times charge. Since I already rearranged my equation to the form I like, I will substitute it in 2. So that's potential difference times charge is equal to force times distance. And now I have an expression where I know that F should be, so I will substitute equation 3, in equation 2 now, my rearranged equation. So that will leave me with VQ is equal to EQ times D. Q and Q are the same, so I divide both sides by Q. And that leaves me with V is equal to the electric, so potential difference is equal to electric field strength times distance. So that's potential difference, so that's electric field strength. And that's the distance between the plates. We already said that this is only for uniform electric fields between two parallel plates. So electric field strength is the potential difference per unit distance between the two plates, basically. We always measure potential difference in volts. We measure distance in meters. This means that the electric field strength can be also rewritten with units potential difference per meter. We also saw it before, written as newtons per coulomb. So there's 2 units that we can use for electric field strength. Now there's an example question here. So the separation between 2 plates is this much, so that's the distance between the 2 plates. And the potential difference is 3.6 kilovolts, so 3,600 volts. Calculate the acceleration of an electron between the plates. So by the way, just to remind you, we already know the charge of an electron is given to us, and we also know the mass of an electron is given to us. So very good thing to always do is to write down all your values that you have and that you already know you have, especially if it talks about electrons, protons, neutrons, and things like that. So from firstly looking at this question, I know that I have potential difference in the separation between the plates, which means I can measure the electric field strength, which would be 3,600 divided by 1.2 times 10 to the minus 2, which will give me 3 times 10 to the 5 volts per meter. But I also know that I need to calculate acceleration. And I know that one of the easiest equations to use for acceleration, since something is accelerating, I know there should be a force. So a resultant force. So F is equal to ma. I calculated the electric field strength, but I don't know the force. And I also know that E can be given to me using force per unit charge. In this case, I know E. I know the charge because it's the charge of an electron. And I need to calculate the force. So what I will end up with is force is equal to E times E, the elementary charge, which is 3 times 10 to the 5 times the elementary charge, which is 1.6 times 10 to the minus 19. If you forgot about elementary charges, please go back to chapter 8 lesson. That's where we first introduced it in AS content. That will give me a force of 4.8 times 10 to the minus 14 newtons. So I calculated the force that acts on the electron, and I also know that F is equal to ma. Since I've calculated the force, and I know the mass should be the mass of an electron because that's the object that's getting accelerated. So that should leave me with acceleration is the force divided by the mass of the electron. 9.11 times 10 to the minus 31, if I'm not wrong. And that will give us 5.3 times 10 to the 16 meters per second squared. So that's the acceleration of an electron between those two plates that have a high potential difference. And if that kind of also should remind you a little bit about the electron gun, which we have come across in chapter 9. I think that's lesson 2, or if I'm not wrong, there's also a video on that if you've forgotten it. I think lesson 1 or lesson 2, I don't remember exactly which one it is now. But if you forget this kind of thing, so the electron gun is quite connected to this topic, and it could come up together as a synoptic link question. Okay, so now we have spoken about uniform electric field between two parallel plates. We also compared the parallel plates to a capacitor. So this is the best point to introduce a new equation of capacitance that is linked to the distance between the plates. So the capacitance of a parallel plate capacitor depends on the separation between the two plates, so distance d, the area A of overlap between the two plates, meaning if one plate is shifted more to the one side of the other plate, then we only take the area that overlaps between them, and the insulator or dielectric material used between the plates. So for the capacitance in vacuum or air, meaning that there's no material, it's just simply vacuum or air, we can use this equation. Now this equation says that the capacitance And don't confuse the C with the unit of charge, coulombs, okay? That's a very common mistake. Capacitance measured in farads is equal to the permittivity of free space. So epsilon naught stands for the permittivity of free space, which I've spoke about briefly before in the first lesson, I think. The area of overlap between the two plates, and we said the divided by the separation between the plates, which is measured in meters. This is in meters squared, and permittivity of free space is farads per meter, or it could have a different unit depending on which equation you're using. Now, this is only for vacuum or air. And this equation is given to you in the formula booklet. It's given to you under the capacitance topic. So don't look for it in the... Just remember that electric fields and capacitors go together. So whatever equations that you might need to use could be in both sections of the formula booklet given to you. Now, if I was using a specific insulator between the two metallic plates or a dielectric material, we have to use this equation. You're going to say, but it looks similar. It is very similar. It's just instead of using the permittivity of free space, we use the permittivity of the insulator. So epsilon stands for the permittivity of the insulator, which is simply the permittivity of free space times the relative permittivity of that material. And that will give you the permittivity of the insulator. You do not need to know why we're multiplying it, which is not hard to explain, but if you want me to go through it, just let me know. And you're not even expected to understand fully permittivity, but because I don't want you to learn something that just by memorizing it, I will just describe simply of what it can be perceived as. So electric permittivity is a measure of how well molecules in a substance align, or otherwise known as polarize, under an electric field. So the higher the electric permittivity, the better the molecules polarize and the more the substance resists the external electric field. So if I were to compare it to conductivity, so we know conductors allow electric charge to flow through it. So when we talk about electric conduction, we talk about how easily a substance allows electric current to pass through it. In this case is how an electric field is capable of passing through a substance. So electric permittivity measures how electric fields interact with a substance. You don't need to know too much about it though, so don't worry too much about it. If you want me to go through it in class, just let me know and I will do so. So before I continue to anything else, let's have a look at an example. So it says a capacitor is made from a plastic bean bag. So that means that we have an insulating material, insulator, a sandwich between two sheets of aluminium foil. So we already know here that we have a capacitor. We have two metal plates and a plastic bean bag between them, which means that we have an insulator. And it gives us the size of the foil bags in centimeters. We want them in meters. The bean bag is also this thick, which basically tells us so this can be used to get the area. This can be used to get the thickness or the separation between the plates. And then it says plastic has a relative permittivity of 4. So my relative permittivity is 4. That means I need to also use the permittivity of free space, which I'm given in the formula booklet. And then it tells me to calculate the capacitance. So my area will be 0.6 times 0.3. My separation between the plates will be 0.08 times 10 to the minus 3. And I can use this equation to calculate it, where I know that epsilon is epsilon naught times epsilon r. So if I simply place the numbers in, I have the permittivity of free space, which is, sorry about that, 8.85 times 10 to the minus 12 times 4 for the relative permittivity of plastic, times the area, which is 0.6 times 0.3, and then divided by the separation, which gives me, if I look at my numbers, I'm given values to two significant figures, so my answer should be to two significant figures, which is 8.0 times 10 to the minus 8 farads. The answer was 7.965, but since it's two significant figures, I have to round it, and that's rounding it to 8. That's it in terms of calculating it. Now we're gonna have a quick look at an experimental method, and then I will be analyzing particle motion between two plates. Okay, so how would I be able to calculate the permittivity of free space if I wanted to determine it experimentally? So if I wanted to determine epsilon naught, I know that this equation, this value is linked to this equation. That means I will have to find a way to measure capacitance, area, and separation between plates in order to calculate the permittivity of free space. The best way of doing that is connecting two plates to a power supply to firstly charge them. So if this is the positive charge, I'm going to call this a flying lead. So I can move it between that and a coulomb meter. So I can use a coulomb meter. That can be used to measure charge, because we know capacitance is the charge per unit potential volt stored across it. So what we have now, that flying lead can be moved once I charge the plates. So that will have an overall positive charge, that will have a negative charge. And I can move the flying lead to the coulomb meter to measure the charge going through them. I also need a potential voltmeter, or even the power supply. If I use a power supply, I can fix the potential difference value. So yeah, I'll change the potential difference. I'll move the flying lead. I can measure myself. We can measure ourselves the separation between the plates. So that will give us, and we need to get repeated values and average them. You will also need to measure the cross-sectional area of the plates that you're using by taking the length and width, or if it's a circular plate, then you need to take the diameter at different directions, diameter or even radius, depending on, what would make you feel that it's going to be accurate enough. But the idea is that you make multiple measurements of that just in case, and record it and average it, and then take the mean value. So you will get D and A easily, but for capacitance you need to record voltage and potential difference and charge for different values, so you can get an average of capacitance. And once you get the values, you can plot a graph of Q against V. So I can rewrite this equation as Q over V is equal to epsilon naught A over D. if I plot Q against V and compare it to the equation of a straight line, so that will be y is equal to mx plus c, it will be Q is equal to epsilon naught A V over D. So that gives me my y will be the charge, gradient will be epsilon naught times the area divided by the distance. V is your x. I don't have a y-intercept, so it should go through the origin. And my gradient is equal to epsilon naught times the area of overlap divided by the separation between the plates. So if I want to find epsilon naught, we already spoke about measuring A and D. So that will be epsilon naught is equal to gradient times the separation divided by the area. And you'll be able to get it mathematically through an experiment. I hope that makes sense. If you do have questions, to ask me in class. Okay, so we have talked already about the uniform electric field and how to prove this equation. We spoke about parallel plates and permittivity for a capacitor and how to calculate its capacitance when you have area, permittivity, and the separation. And now we're going to look at the motion of charged particles in a uniform electric field. This is where SUVATs will be introduced back again to remind you, and I will also talk about the important parts to use for this topic. Okay, so what we're going to look at in terms of motion of charged particles in electric fields. There's two motions that we're going to look at. So first is by, the first thing is placing a stationary charged particle in an electric field, in a uniform electric field. And the second one is basically letting it move into an electric field at right angles to the direction of the electric field. So it's already moving at right angles to electric field. So we start first with placing a stationary charged particle, and then we're going to proceed with that. So every time we place a charged particle between the plates, the charged plates, basically in an electric field, it will either travel towards the positive or negative depending on its charge. That means it will experience a force, and this is going to be a constant force since we have a constant electric field strength. The electric field strength doesn't change, which means the charged particle will experience a constant electrostatic force, which also means that it will have a constant acceleration. So here we're going to start looking at some things to use constantly. So, for example, when we solve these problems in between uniform charge plates, you have electric field strength is potential difference divided by separation. So it's one of the important things to remember. Also, the electric field strength in terms of force and charge, and the work done on the charged particle to move between the two plates. Other equations that can come very useful in this topic is F is equal to ma, and any SUVAT equations, depending on what we're looking at. Firstly, we won't be using SUVAT, we could use SUVAT equations for both actually, so I won't cancel that out completely. So firstly, let's talk about the motion of a particle between plates. If I placed it, so these are our plates. If I connect them to a negative and positive terminal, so they will have a specific PD between the two terminals. we know the separation between them. So if I placed, so this will have positive charge, sorry. This will be negatively charged. If I wanted to draw my electric field lines, they should be equally spaced to show uniform electric field. So from positive to negative, remember that. Now if I placed an electron, let's say I took an electron and just placed it there. Now we know that electrons are attracted to positive terminals. So the electron will go from being stationary, so from 0, to speeding up towards the positive plate, so against the direction of motion, direction of electric field, sorry. And yeah, so it will accelerate towards there. We will do an example question together to explain some other things as well. But even in the case that you have something accelerating, so the electron is accelerating from the negative to the positive terminal, sometimes you can also make electrons decelerate. So if they are to decelerate, it means that they're going to have to move towards the negative terminal. So if it was to force to move towards the negative terminal, it will decelerate because it's being repelled. It's the same thing as, for example, if you throw a ball upwards against the gravitational field, it will decelerate up to a specific point, then stop moving, and then come back. But if you were throwing something towards the floor, it would just accelerate towards the floor. So it's quite similar in terms of gravitational and electric fields and the motion of charges and masses within the two fields. So let's continue to the example. So it says you have an electron. Once again, we always know the charge of an electron and the mass of an electron is fired from a positive capacitor plate towards the negative plate. So you have positive, you have negative. So the electron was fired from the positive towards the negative. That means it will be decelerating. It's also telling you the initial velocity was fired at. So that's u. The potential difference is 600 volts. So it gives you the potential difference. Sorry, it's a capital V. It also gives you D, which is 3 times 10 to the minus 2, or 0.03 meters. This says calculate the maximum distance the electron will travel. That's because, so S, that's because we know that the electron will go as close as possible, and then it will stop moving and reverse its direction and go back towards the positive terminal. That means that I will have to identify the point where the electron will reach the maximum height, stop moving, and then turn back. That means I know that the final velocity should be 0 in that case. So if I write down my SUVATs, this is the distance I need to calculate. This is given to me. I know that that should be 0 just because it has to go against its direction of motion. So it won't be able to reach fully all the way to the negative terminal. And I can calculate the rest. I can calculate the acceleration here. Since I already know the potential difference in the separation, so we know that E is V over D. I also know the mass of an electron, so F is equal to ma. I will combine the two equations as well. So, and I also know that E is equal to F over Q. So I will combine these three equations. So that's 1, 2, and 3. F, I'm just going to equate them together. So we'll equate 1 and 2 together. So F is equal to VQ over D. I know that the charge of an electron is the elementary charge, so I will just rewrite it as F is equal to VE over D. I also know that F is equal to MA, so I will substitute equation 3 in there. So it will be MA is equal to VE over D. I'll divide both sides by M, which means I'm left with acceleration is potential difference times the charge of an electron divided by the separation between the plates times the mass of an electron. Once I place, and I have all these values, I know the charge of an electron, I know the mass of an electron, I know the potential difference, and I know the separation. So I'll put all the values in. You could do it step by step. So you could first calculate the electric field strength, then use electric field strength is equal to force divided by the charge to calculate, so rearrange it to calculate the force, and then you can use F is equal to MA to calculate the acceleration. It's all up to you if you want to do it step by step. I usually prefer to get things done in one go and put the values in one go instead of using my calculator constantly. Just rather use it in just a simple go. So that should give me a value of 3.513 times 10 to the 15 meters per second squared. So there you go. There we have it. We calculated the acceleration. So I have four values. I have four values, 3 known and 1 unknown. I don't care about the time because remember in every SUVAD equation, there's 4 variables linked together with 1 unknown. The one that suits it best is v squared is equal to u squared plus 2as. We know that v is 0, so that's gone. And then we have u squared is equal to minus 2as. We also know that the electron is decelerating, so it will have a negative value, and that negative value will cancel out with this negative value. So I'll just do it. We need to calculate the distance, so that will be minus u squared divided by 2a is equal to the maximum displacement or distance the electron traveled. So that is 1 times 10 to the 7 squared divided by 2 times minus 3.513 times 10 to the 15. As I said already, because it's minus and minus, they cancel, it becomes positive. So the distance will be equal to 1.4 times 10 to the minus 2 meters. So it was a bit of a long calculation, but the more you get used to linking values together, especially these type of equations, it will get easier. So this was just simply me placing a charged particle and or shooting it in the opposite direction that it should be going, but it will be already within the field. Now there's another possibility that you will be shooting charged particles at right angles to the electric field, and we're going to have a look at that now. So this is what we see in terms of charged particles at right angles to the electric field. So consider an electron being shot at right angles. So this is right angle to the electric field. So you must remember what we have seen in, what you have done with your other teacher in projectile motion. This is what we see here. We have projectile motion because you have an electron accelerating towards the positive terminal. So you can see the electrons accelerating towards the positive terminal. But since it was already moving in this direction, you have a component of motion in the direction perpendicular to the field, as well as a component, so perpendicular to it, as well as a component parallel to the field. And we also know that in projectile motion, the perpendicular and parallel components of motion are independent of one another. So this motion and this motion are independent of one another. The only thing they share is the same time it takes for the charge to go from here to here. So along which axis is it accelerating? So if you look at the diagram yourselves, you know that it's accelerating downwards because it's going towards the positive plate. So it's always accelerating in this case, well, y-axis, the way it's drawn. And along which axis does it have a uniform speed? From what you already remember from your is it chapter 5 or chapter 4? Or is it? Let me double check. I think from chapter 3 and chapter 4 as well. Oh, chapter 3, sorry. So that's chapter 3, the very first chapter that you've done in physics. So along which axis does it have a uniform speed? It should be the x-axis. So the speed of the component of speed in the x-axis does not change throughout this motion, but in the y-axis accelerating downwards, so it is. So this is a simple diagram, a simple list of things that happen. Let me just try and get the picture in as well. So the vertical motion that it's talking about is the x-axis. Oh, sorry, the y-axis. The x-axis is the horizontal. So if you notice there is no acceleration, so the horizontal velocity is constant, meaning that the only equation that we need to use here is the displacement divided by time. There is no acceleration, so A is 0. Remember that bit. And in the vertical motion, it's accelerating due to the electric field, which means that we can use suvats for it as well. So if I start drawing on the diagram, the horizontal part of the velocity will always be the same wherever the particle is, but the vertical speed will be changing, especially increasing, since it's accelerating as the particle's moving. Now we know that acceleration is F over m, and in our case F is equal to the electric field charge times the charge of the particle. By the way, it won't always be electrons, okay? Any charged particle can be tested. So it could be a question about electrons, question about protons. It could be an alpha particle, which is 2 protons and 2 neutrons. You do need to take into account their masses or their charges. So in this case, it will be 2e for the alpha particle as charge. Its mass will be 2 protons plus 2 neutrons worth of mass. This will be the mass of a proton, and e, positive value of e, which doesn't really matter if it's positive or negative in our calculations, unless we need to state whether it's attractive or repulsive. And the same thing here. We usually have everything that we need as long as you remember to use the right ones. Don't memorize that you have to use the electron mass or the electron charge at all times. It could be that you are finding it for a nucleus of an atom or something like that. So be careful. So yeah, if I combine the two, I have EQ over m, which could give me the acceleration due to an electric field. That's if I obviously have the electric field strength, the charge, and the mass. Now, if I'm not given much about the electric field strength, if they give me the potential difference and separation between the plates, I can actually calculate it using this equation. At all times, don't forget that the initial vertical velocity is 0. So before the particle starts accelerating downwards, it's initially moving in this direction. So here we have this part will be 0 to begin with, the initial vertical. So UV should be 0 meters per second. And I can use SUVATs to find the vertical component velocity as it exits the field. Usually we can use any SUVAT equation depending on what it gives us. But if we have to use this one, remember we said already that that's 0. So V is equal to acceleration times time. Now, time, if we consider the length of the distance, as the distance moving in this direction. So we know that time is distance traveled divided by the horizontal speed. But in case of a specific distance, we can input now the values as V vertical is equal to the acceleration, which we stated here, EQ over M, and times it by the time, which is the same. That's the only common thing between them, the time spent passing length L. So let's say L of VH. So that's times that time, which is L over V horizontal. So I can find V vertical using this expression. Now, nothing of this is given to you in the exam. You are given every other equation that you have to use to figure it out. But please don't try and memorize it, because sometimes you might not need to calculate that. You might need to calculate something else, and then you will come unstuck. Now, as a quick reminder, don't ever forget to calculate the total speed at a single point by using Pythagoras. Many people forget to do that. So sometimes they calculate the horizontal speed and the vertical speed just about when it exits the plates. But it asks to calculate the final velocity of the particle, which means that you need to use Pythagoras to find the basically the final speed of it. And also the direction, which you can use sine, cos, or tan, depending on what you're given to calculate it. We will do examples of this in class. I do expect that questions like this will show up in one of the 3 papers. But yeah, more practice, the better will come. I'd absolutely love these questions though, and we'll have a bit of fun doing them. So if you have any questions to ask me, in the meantime, make note of it and I will get to it.